I have to admit that there is no deep, important, meaningful significance to exercise 8. However, what I really like about math and using computers to learn math in Python is just rearranging things. So it's one way to get familiar with an equation. So you start with an equation. Maybe it's an equation that you kind of understand or you're a little bit familiar with, or maybe you just don't understand it at all. And just try to move things around and see if that helps you make sense of the equation. So for example, you could divide both sides by lambda. As long as lambda is not equal to 0, I don't know, maybe that helps you understand this relationship. Or you can invert A and isolate V on this side and put A over here. Or you can move V over here. Now, we cannot just invert V because it is a vector. There is no inverse of a vector, but there is a pseudo-inverse of a vector. So now that you know about the pseudo-inverse of a matrix, you can think of a column vector as an m by 1 matrix and compute its pseudo-inverse. And yeah, that just allows you to kind of play around with these equations for a little bit. And that is the principle that I really enjoy and I encourage you to do. Okay, so the 2 by 2 matrix used at the outset of chapter 13, it's just a integers matrix. It's just convenient to work with because it's all integers, I guess, as easy to interpret eigenvectors and so on. Okay, compute V pseudo-inverse and confirm that V times V pseudo-inverse is 1. And then just explore the following identities. Really, all I'm doing here is just playing around with this equation. Again, there's no deep theoretical significance to these equations. I'm really just trying to encourage you to come up with ways to use Python to keep exploring concepts in linear algebra and statistics and machine learning on your own. So here we have the matrix. It is a 2 by 2 integers rank 2 matrix, so we know it's going to be invertible. And here I take its eigendecomposition. This is just to get the eigenvalue. We're particularly focused on one eigenvalue and one eigenvector. And then I'm multiplying. So this is the left-hand side of the equation. This is the right-hand side of the equation. And yeah, we can just print these things out. I'm transposing here only so that they come out as rows. Just makes it a little bit easier to visualize. Okay, so this is just confirming the eigenvalue equation, right? So m times v, or a matrix times the eigenvector, equals the eigenvalue times the eigenvector. So just a nice empirical confirmation here. Okay, here I'm checking that v times v pseudo-inverse equals 1. And that is the expected result because a matrix times its inverse should give us the identity matrix. Now, for a vector, we don't have a matrix, so we're going to end up with the identity 1 by 1 matrix, which is just the number 1. Okay, here we get to the first equation that I showed in the book chapter. So this is basically a quadratic form on the matrix M with V pseudo-inverse to the left and V to the right. And then, yeah, that is the same as just the pseudo-inverse times the vector itself scaled up by the eigenvalue. And you see that those two are the same. Again, this is not surprising, right? Because this is what the math tells us when we manipulate the algebra. So it's nice to get this confirmation in Python. This improves your math skills, it improves your coding skills, and so on. Okay, and here is that second equation where we're creating outer product matrices between P and P inverse and M. So of course, this is a matrix, and this is also a matrix, and here we have the matrix and the eigenvalue. Again, the conclusion here is not that the matrix equals the eigenvalue. The conclusion is that the impact of the matrix on this matrix is the same as the impact of the eigenvalue on this matrix.